Good day, I'm Norman Wildberger. We're having another look at arithmetic, the foundations of arithmetic, the fundamental basis on which modern mathematics is built. And it all comes down, of course, to natural numbers and the arithmetic with natural numbers. And this turns out to be considerably more subtle than it's usually thought of, because we've appreciated now the huge complexity involved in larger and larger numbers. This is a key insight that we have been developing. So we know now that just to hope that the kinds of experience and understanding that we have developed for smaller numbers, the hope that that just extends in a natural way to all natural numbers is misguided. Okay? We have to think carefully about the scale at which we can legitimately and logically comprehend, define, and prove our arithmetic is valid. So the reality is probably that the currently regarded theory of natural numbers is too wide. It's too ambiguous. It's too all-embracing. We need to actually be a little bit more careful in prescribing different aspects of the things which are now currently just clumped together. In particular, there's at least three notably distinct levels at which we can try to access what natural numbers are. At the primitive natural number level, where we just regard a natural number as a M set of marks, and we oblige ourselves to actually write down such an M set explicitly and completely in order to have the natural number. And that's a reasonable type which we have some familiarity with now. That's NAT. And then there's the Hindu-Arabic natural numbers, the most familiar ones, of course, to us, where we write down something like this, 3,793. And we're going to move to try to understand what that's all about in today's video. And we're going to try to move towards establishing some kind of definition for this other type num, which is distinguished from NAT. But there's also this third level, which we're aware of, the arithmetical expressions for natural numbers, where we're allowed to concoct expressions involving arithmetical operations, simple ones like this, or maybe even more complicated ones like we've been looking at. And these are also candidates for numbers, but they're definitely different kinds of objects than these ones. And these ones are different kinds of objects than these ones. And they all have different sort of scales at which they're more appropriate. Okay, that's an important thing to realize. That relatively small numbers are well captured with this. Sort of medium kinds of numbers are captured with this. And very large numbers, you have to go to some system like this. It's like Papa Bear, Mama Bear, and a Baby Bear kind of numbers. So we've had a look at primitive natural numbers, and we've seen that they have a simple arithmetic, which is very easy to understand and easy to compute with, and that even relatively small children can understand sort of why this kind of arithmetic obeys the simple, important arithmetical laws that it does. When we go to Hindu-Arabic numbers, it's really a quite different story. Okay, so it turns out this is already a very subtle issue about how to set up a theory of Hindu-Arabic numbers. And we'll see here that there is at least three different ways of introducing them. At least three different ways of orienting our approach to Hindu-Arabic numbers. Now, we have to say, of course, and have to recognize that we are so familiar with the Hindu-Arabic system. Right? Because we've been taught this system from a very early age. And we have spent hours and hours, hundreds of hours practicing, learning, seeing applications of this Hindu-Arabic system. So it's really almost hardwired into our mental frameworks. And we shouldn't take that for granted. Okay? It's actually not a replacement for a solid, logical foundation for what actually these things are. So that's what we're looking for here. We all know that we can, do Hindu-Arabic arithmetic, at least for relatively small numbers where the calculator is not needed. But what exactly is a Hindu-Arabic number? And what exactly are the definitions of addition, multiplication, and so on? And how does one actually prove the laws of arithmetic for these objects? That is what we're interested in here today. So our first approach to possibly setting up Hindu-Arabic numbers is to regard them as short forms for primitive natural numbers. That they provide us with a convenient way of concisely expressing these primitive natural numbers, which can be quite onerous to write down and express. So what we do is we look at the primitive natural numbers and we give them the usual names. So this one here, called 0, and we give it the alternate symbol that we're familiar with. This thing here with a single mark in it is the number 1 with its usual number. This is 2, this is 3, and so on. This thing here would be 27, written like this. Okay, we're all very familiar with the system here, but we know that it does take some explaining. I mean, to actually explain it to someone who didn't know what it was about, we'd have to talk about how we take one of these big M sets of marks and subdivide them into ones, tens, hundreds, thousands, and so on, and then count the numbers of those various things and then string them together in our sort of Hindu-Arabic list. So if we proceed this way, and this is a valid possible way of proceeding, okay, that a Hindu-Arabic number is just a short form for a primitive natural number. Then the definition of operations on Hindu-Arabic numbers simply reduces to those of the primitive natural numbers. It's just a reflection of this prior arithmetic that we already have in place for the primitive natural numbers. So instead of saying 1, 1, 1, 1, 1, 1, 1, 1, 1 plus 1, 1, 1, 1, 1, 1, 1, 1, 1 equals 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, or something like that, we might rather say 9 plus 13 equals 22. Okay, it's just a shorthand for it. So logically then, nothing really too much in addition is required. So if we do take this approach, then Hindu-Arabic arithmetic is completely equivalent logically to the arithmetic with natural numbers that we already have, the arithmetic with primitive natural numbers. And we can flag this usage in the following way. So let's write the following, that if we write 7 is of type nat, okay, what that means is that 7 is defined as this thing here. So this is the actual object in nat, and when we write this, we agree that this thing here is defined to be this. In other words, this is another name for this. Okay, why don't we do this then? And end of story. Because there's a serious disadvantage with this. But it's a logical disadvantage that really only becomes apparent once we step outside the bounds of familiar, relatively small arithmetic. The disadvantage is that we are logically restricted to numbers less than 10 to the 200. Why? Because this is the maximum possible size of a primitive natural number in our universe, roughly. We've seen that if you want to write down a bunch of ones or marks, okay, the very, very most that you could do that is determined by how much room there is in the universe and how small you can write. And if you're writing at the very smallest scale, which is, let's say, the Planck scale, and you're writing to fill the entire universe, then we've decided that there's roughly 10 to the 200 such little Planck cubes filling our universe, very roughly. Okay, and that's then an upper bound for the number of marks that you can make. Of course, you could never make anywhere near that many marks, but at least in principle, we can contemplate something like up to that amount. Okay, but we are constrained roughly somewhere at this level. Right? We are not able to conceptually even imagine in our universe M sets of stuff with a lot more than this number. For example, these various numbers that we've been talking about, Z or Z prime or 3 star n squared 4, Right? These numbers are so big that they completely overwhelm the possibility of actually exhibiting an M set with this number of objects in it. Okay, so that means that if we're going to attach our Hindu-Arabic numbers to primitive natural numbers, then we are constrained by whatever bounds we have on the primitive natural numbers. And we are constrained because the universe is probably only so big, and we can write probably only so small. So let me illustrate this point by giving you an example of something that's arithmetically impossible for us, even though we would actually want it to be possible. So consider the question of adding this natural number to 1. This is the natural number 96511. I'm not going to tell you all of it. Okay, you can read it there. It's a natural number with roughly about 200 digits. Therefore, this natural number is so big that it represents the size of a set or a multiset, which is impossible to conceive of in our universe. We cannot write down and exhibit, even theoretically, even in principle, an M set or a set which has this number of objects in it. So if we're thinking about this as representing a primitive natural number, we are just stepping beyond the bounds of what we actually can do. So we would have to look at something like this and say, I'm sorry, this does not make any sense, because we cannot interpret this thing as a primitive natural number. But this is too limiting for us. This is too limiting. We want to be able to make calculations like this, because we all could make this calculation, right? The end of doing this is you just change that 3 to a 4. Our computers can deal with numbers which are this big. They can do all kinds of great computations with them. And if we're doing geometry in a sort of integer framework, or rational number framework, once you go a few steps in complexity in some actual specific situation, you're actually making computations, then you shouldn't be surprised to have bigger and bigger numerators and denominators occurring. That'll typically be what happens. Okay? When you make the addition of fractions or multiplication of fractions, then the denominators and the numerators generally get bigger. So every time you make a computation, then you're increasing sizes. And so it doesn't take that long before we can realistically end up with numerators and denominators that are of this order. We want to be able to deal with them. We don't want to just throw up our hands and say, I'm sorry, that's no longer supported by our theoretical constructs. So we want to do bigger arithmetic, and so we need to free num from nat. We do not want to identify these two things. We do not want num to just be a replacement or a short form for nat. That's too limiting. All right, so notice how this understanding really does depend on our investigations of bigger numbers and our investigation about complexity, right? We've been thinking about complexity. We have this sense that, there's limits out there in terms of how big you can write down expressions, and correspondingly how big are the numbers that you have some realistic hope of writing down in some fashion or another. All right? So we're trying to address that. We're not pretending that we're living in some unicorn kind of universe where there's an infinite amount of room and we can just do infinitely many things just by waving the hands around. We're not doing that. We want to really pin things down solidly. All right. So what we want to do is we want to free num from that. We want to have our Hindu-Arabic number system allow us bigger arithmetic than we can do just with nat. Nat is great, but we want to do something more. All right, so let's look at a separate line of inquiry. Let's think about Hindu-Arabic numbers as a separate system from nat, but which correlates with it. So that's our aim, to try to see some direction in which we could create a theory of natural numbers based on Hindu-Arabic representation. Okay, so this is a lot more work. This is a lot fancier than dealing with primitive natural numbers. It's several orders of magnitude more complicated, in fact. In fact, I claim it has not yet been done. In 2016, there's no place where you can find a proper theory of Hindu-Arabic numbers. In particular, piano-type axioms, some of you will have heard of an axiomatic approach to numbers. So piano axioms don't really help us either, because piano is resting on the idea of building up natural numbers by successors. And if you want to start with 1 and then you add 1 and then you add 1 and then you add 1 and so on, and you want to kind of build up an arithmetic, you're really essentially in the realm of primitive natural numbers. Okay, so piano is just an axiomatic approach to what we're calling natural numbers. In fact, it doesn't really aid us considerably, but we'll talk about piano at some other point. But in any case, piano is not going to help us going beyond the primitive natural numbers. We need to do something else. We need to go beyond this need to have our numbers connected with an actual M set or a sequence of things that we can write down starting from 1. Okay, so here's a rough outline of how to proceed. So here's a program that somebody could think very carefully about and work towards creating a theory of Hindu-Arabic numbers. Isn't it remarkable that in 2016 such a program is possible? That there's this road that could be gone down by somebody who's careful and serious enough and really wants to do some work to establish arithmetic. That's what we're talking about. It's not some tangential thing built on top of the extremities of a theory, built on the extremities of some other theory. Right? This is core mathematics we are discussing here, isn't it? Okay, so how could we start? We could start by defining Hindu-Arabic numbers as expressions like this. Okay, that's not so hard to do. So a Hindu-Arabic number is an expression like this. And what does that mean? Well, it's a list, or if you like, a string of digits. The digits are all taken from this set, the usual ones, 0 to 9. And the strings have the property that, well, they can be arbitrary, except for the rule that they can't begin with 0. They can't begin with 0 except for the single number 0 itself. That's the only number that can start with the digit 0. By start, I mean the leftmost digit is 0. And all lists must be non-empty. We're not allowing any empty lists. All right, so that is a reasonable definition of what a Hindu-Arabic number is. And we could agree that you have a Hindu-Arabic number precisely when you can write down such a string. You can write down a string like this one, you have a Hindu-Arabic number. So we don't need to suppose that there's some set somewhere that this is counting. Okay? The Hindu-Arabic number is just this string that we write down. That is a very sensible and concrete and reasonable way of defining these things into existence. That'd be like step 1. Okay, so now that we have the objects, the numbers themselves, we are obliged to define the operations. So, say addition and multiplication, the two ones that we usually start with. How are we going to define these? So note that now it's no longer possible for us to go back to the natural numbers. We can't say take your Hindu-Arabic number and find an M set or a collection or a set that has that many objects in it, and take your other Hindu-Arabic number and find another M set that has that many, and then dump them together and then count how many we have. Okay? That works only if we're in the realm of possibilities for exhibiting these M sets. And we've already sort of flagged that we are going beyond that. Okay? So we cannot rely on just converting our Hindu-Arabic numbers to natural numbers and working there. But nevertheless, we can still connect with what we're doing with natural numbers. So we could create addition and multiplication tables. Okay, and so here's an addition table for just the digits themselves, and here's a multiplication table for the digits themselves. Well, the tables are not complete, but I'm sure you can all complete them. Okay, so one could sort of write down these tables and say, this is how we're going to define the addition of just our Hindu-Arabic numbers, which are given by single digits. If we want to know what is 2 plus 6, we look under the table and we say, it's 8. If we want to know what is 2 times 7, we look under the table and we say, it's 14. Okay, so of course this table doesn't tell us how to add more generally, but it's a start, okay? So we give these tables and we define the operations on the single digits this way. And of course we all know that these things do come from our understanding of natural numbers, the primitive natural numbers, and how addition and multiplication work for them. But in fact we don't really need to say so. Okay, we can just say, here are two tables and we're going to define addition and multiplication by these tables. That's how we tell our computer how to add digits. We don't have to explain to the computer where we got these things from. All right, so now for the second part of that second step, we need to extend our understanding or a definition of addition and multiplication to general Hindu-Arabic numbers. Okay, because we've had lots of experience at this in primary school, we know, at least in principle, how this should proceed, or roughly anyway. Because we know how to use those addition and multiplication tables to add and multiply more general numbers. If we want to add 2, 3, 7, and 49, we know that we start on the right and we add 7 and 9 using the table. We get 16, we write the 6, we put the 1 up there, and then we add 3 and 4, we get 7, and we add the 1, we get 8, and then we bring this 2 down. If we want to multiply 2, 3, 7 by 4 and 9, well, we multiply 9 times 7 is 63. We write the 3, we put the 6 up there. Then 9 times 3 is 27. We add the 6, that's 33. We put a 3 down, there's a 3 that's coming up there, etc. All right, so it's a question then of taking the familiar knowledge about how to actually add Hindu-Arabic numbers and telling our computer how to do that. That's essentially what the definition is. So extending our definition from single digits operations to general string operations. All right, so this is a fair amount of work, but it's not impossible. You could certainly program a computer to do this. And in fact, if you look at computers that do have code that works on Hindu-Arabic numbers, well, they have something like this. Right? That's what they do. And then we have a third challenge, which is to prove the laws of arithmetic. This is more challenging than you might think, because you are not allowed to use the prior knowledge of arithmetic with natural numbers, with primitive natural numbers, okay, except for small numbers. So we can use the fact that for small numbers, we know that 3 plus 7 plus 8 is the same as 3 plus 7 plus 8. So we can use those things, but we don't know that associativity, or say the distributive law, or even commutativity, is necessarily going to be operating on these huge Hindu-Arabic numbers. Of course, we have this intuition that they will, okay? But it's not a valid argument to say, well, we just convert these big Hindu-Arabic numbers to M sets, and then we do the primitive natural number operations there. We know that things are commutative or associative or distributive there, and then we go back up. That argument only holds up to the limits of our natural or primitive natural number system. And we're proposing to go much beyond that. So we need separate, independent proofs of the laws of arithmetic. Can you appreciate that there's something to be done here? And it's actually a considerable amount of work. And it's not at all immediately obvious what the most efficient and elegant way of doing this is. This will be a great master's project, I think. Right? A student could easily spend a year or two thinking about how to do this really in a nice, elegant way. It'd be very instructive. Okay, and so if we went down this road which I'm broadly outlining here, we could put that together and then get a new system which we could call NUM, Hindu-Arabic numbers, which extends the arithmetic of natural numbers and coincides with it when there's overlap. So you've probably guessed that that's not how we're going to proceed. We're going to proceed down a different path. So this is the third approach that I want to suggest to you in terms of establishing an arithmetic for Hindu-Arabic numbers. So I propose that Hindu-Arabic numbers can be viewed as multisets. And when we take this M-set point of view, then we can exploit things that we already know, and we can create an alternate form of the Hindu-Arabic arithmetic. But it will require us to think a little bit differently. So we have to be prepared to shift our orientation a little bit, but you're used to that anyway in this channel, right? Okay, so the motivation for this is the following. Suppose that we take a Hindu-Arabic number like 43, which of course is 3 plus 4 times 10 to the 1. So in terms of powers of 10, which is naturally what's going on here, it's 3 times 10 to the 0 plus 4 times 10 to the 1. So here's another way of representing that information as an M set. So here's an M set. It's got square brackets and no commas. And it's got repetitions. There's 3 singletons here, singletons with zeros in them. And there's 4 singletons with 1 in them. Right? So these are just like lists with 1 element. And there's 3 zeros here to represent the fact that there's 3 times 10 to the 0 in this Hindu-Arabic number. And there's 4 singleton 1s to represent the fact that we have 4 times 10 to the 1 in this number here. So this is maybe rather long, but it is a legitimate way of representing the information contained in that Hindu-Arabic number. Let's say we have a slightly bigger one, like 512. Well, that's 2 times 10 to the 0, plus 1 times 10 to the 1, plus 5 times 10 squared. And then that information can be represented in an M-set point of view by having 2 singleton zeros, 1 singleton 1, and 5 singleton 2s. This is then an M-set which essentially contains the information encoded in this Hindu-Arabic number. And it does so in a way that actually corresponds with what we're writing down. So you could look at this and reasonably easily write down this thing here without having to convert to a natural number. So we're not going via NAT here. Okay, now if we stare at these things, we say, wait a minute, we've seen this kind of thing before. These are just vexels. These are the kinds of objects we were playing around with when we were talking about Maxwell theory, our sort of novel point of view towards matrices and elementary linear algebra. Right, vexels were some kind of M-set replacement for vectors. And they're exactly like this. They're just multisets of singletons. A singleton being a list with a single natural number in it, where a natural number now is allowed to be 0 as well. That's a little bit of a difference from previously. Okay, so the possibility is now to harness our earlier discussion of vexels and that framework, to harness that as a scaffolding to build up a theory of Hindu-Arabic numbers. So we need an arithmetic with vexels. And pleasantly, this then also draws in earlier discussions about polynomials and what we called polynumbers. So we're going to be unifying a whole bunch of things here. Algebra in terms of polynumbers, linear algebra in terms of these vexels, and fundamental arithmetic in terms of Hindu-Arabic numbers are all going to start being part of the same intimately connected story. We'll start on that next time. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.